Firstly, Thevenin's theorem. Again, this is a bit of a repeat of what we covered on this in science, but Thevenin's theorem says any active network having two terminals A and B can be replaced by the constant voltage source of voltage V little t, it's the Thevenin's voltage, and an internal resistance R little t. The value of Vt is equal to the open circuit potential difference between the terminals A and B, and R little t is equal to the value of the resistance of the network measured between A and B with the loops connected and all sources of voltage and current replaced by that ideal internal resistance. Okay, so you may or may not remember that, but you'll remember doing something along those lines for a question in the science assignment. Alright, and we're going to go back over that today. So, what Thevenin's theorem does is take a circuit like the one on the left, okay, and 30 ohm resistor of interest, or what we often call the lead resistor, then you can actually turn the rest of that circuit using Thevenin's theorem, that bit of the circuit, into that with the 30 ohm resistor added on at the end as the output resistor, load resistor. Alright. What that then allows you to do is, if this is the load of interest, you can then analyze the circuit for different values of load resistor, and that part there, this part will act exactly like the green part of the original network for any load resistor. Alright, this Thevenin's is not useful when you're interested in what happens if you change the other. Well, it is, but you'd have to do the Thevenin's process all over again if you wanted to focus on the 20 ohm resistor or focus on the 5 ohm resistor. Yeah, but it's really good when we want to focus on one so-called load resistor for multiple values of that resistance. Alright. Now, if we want to use Thevenin's theorem, there's a process to go through, or a procedure to adopt. Summarised as follows. First, a load resistor, for which we need to analyse the current network, leads to open terminals. We usually mark them A and B. Doesn't matter. Okay. Then, first, determine the open circuit voltage between the terminals after having removed the load resistor of input. That becomes your Thevenin's voltage. Remove source voltage or current, so any voltage sources you take out, any current sources you take out, you replace them with their ideal internal resistances. So that's short circuit for a voltage source or open circuit for a current source. And then we determine the resistance as would be measured between the terminals A and B. So you look back in, what resistance was I measure at A and B, having shorted out any voltage sources and taken out any current sources and left them open circuit. Okay, the result becomes R little t, the Thevenin's resistance. What you can then do, then end up with the equivalent circuit that we saw earlier. So that would be V little t, Thevenin's voltage, R little t, the Thevenin's resistance. There's our two terminals, A and B, and we can connect any load resistor of any value and analyse what current, what power would be, and what the voltage at the terminals was for that load. Yeah. Okay. So, if we have a look at an example, we're going to do is determine the Thevenin's equivalent circuit for that network at terminals A and B, and use the equivalent circuit to determine the current and power for load resistors RL of 20, 40, 60 ohms. Yeah. So once we've gone through that Thevenin's process once, we can then plug in the different load resistors and do a very quick analysis of what the load and load voltage if we want to know power. Alright? So, the first thing we do is to find the Thevenin voltage dt by determining the open circuit voltage. So we need to use any other calculation, normal calculation method we know, to find the voltage across these terminals here. Now you should know that is the same as this voltage across VR3, because there is a Kirchhoff's voltage law loop. We've got one clockwise arrow and one anti-clockwise arrow, so those two voltages must be equal. So if we can find VR3, we've found the open circuit, therefore we've found VT. So how would we do that analysis? How are you going to do that? From the purpose of finding the total resistance, though, Toby, is you can then find the current. Alright, so by all means, if you want to, calculate the total resistance first. So that's 1 plus 5 plus 10 equals 16 ohms. Yeah. Then we can calculate what? Yeah. Because in this circuit, we've got a current flowing I, like that. It's not the current flowing when the load resistor's connected, remember. That would be completely different if we had a resistor connected in there. So I, D, which is 32 over 16 equals 2 amps. Yep. Next, so what we know, the final bit that we want to know is that VR3 is equal to V open circuit, which is equal to V Thevenin's. It's all well worth saying that, where they all come from. You're calculating VR3, but you know that's equal to the open circuit voltage, and the open circuit voltage is the Thevenin's voltage we're looking for. It's equal to I times R3, that is 2 times 10 equals 20 volts. Yeah. So that's finding the Thevenin's voltage. And I noticed in some of the science assignments, people found the Thevenin's resistance first and then went and found the voltage. That doesn't make any difference. They're two separate tasks that can be done independently of each other. Okay, it's just happens that I always seem to go for the Thevenin's voltage first, but it doesn't matter which one you do first because they're two completely separate tasks. So you need to be careful to make sure you keep them separate, because if you use RT again in the other process, it's not the same RT as this RT. Do you get my meaning? Yeah? So you need to make sure when you're doing that kind of thing that you separate out what you're doing and explain it all. Okay, and again in a science assignment, some of you could have done that a bit better. All right, but we'll come with that when I give you the proper feedback soon. All right. So 20 volts is the Thevenin's voltage. We have a circuit. You put one in. What we've done so far is found 3 Thevenins is 20 volts. I'll line this board up in a minute. So we got that far. Now we've got to go back and find our little t. So we do that by proving the voltage source. And because an ideal voltage source has a resistance of 0 ohms, we replace the voltage source with a short circuit. So that's this bit here. And then we've got to determine what the resistance is, looking back in there, i.e. if we got an ohm meter and put it on those 2 terminals, what would we measure? So how do I calculate the total resistance of that circuit? We've got no voltage, we've got no current. How is it connected? What's in parallel with what? Yeah, that is, yeah. But get the meter for a minute. That's confusing the issue. What type of circuit we got there? Series parallel ones. You've got a combination, haven't you? These 2 are in series. That pair are in parallel. Yeah, agree? So if we want to do that, we've got, so for this circuit, RT is, and we can use product over sum, it is R1 plus R2, yeah, series those 2 together, and multiply by R3, and then the bottom will be R1 plus R2. Yeah. Everybody understand that? If you prefer to add these 2 together first and then do product over sum with the result, that's fine. But equally, you can do it in one go like that. That is times, that's a dot there. Yeah. So it's 1 plus 5 times 10 divided by 1 plus 5 10. I think that's 60 over 16, is it not? Ohms. If you want to calculate that into 3 significant units. Is that exactly 3.75? So our Thevenin's resistance, which I will call R little t, so I better be consistent. Calculate it all, but bear in mind, depending on the complication of the network, you might not be able to calculate it all in one go. In this case, and to retain all accuracy. So we can now add that resistor to our equivalent circuit, 3.75 ohms. and we can add in our load resistor, RL, and then we want to analyse for, what was the original question, 20, 40 and 60 ohms. So for RL is equal to 20 ohms, I is equal to, how do I calculate I? Yeah, so V little t over R little t plus RL. I think we can do that calculation in one go. Yeah. That's 20 over 23.75 equals. I've got to say it in 43. That's less than one. Three significant figures. 0.84 amps. Yeah. And power is I squared times RL. 0.84 squared times 20 equals. .84 watts. RL equals 40 ohms. You can do. So, in summary, as compared to the Thevenin Theorem, the Norton's Theorem, if we're interested in a particular branch, we must then take everything out of that branch. If we're interested in that 30 ohm resistor, but in this case we must also take the 5 out. That's why I used this example to make that point. Okay. We then short out the two terminals A and B and calculate the short circuit current flowing. That may well mean the circuit is much simplified because of the short. You need to look at what resistors you're shorting out in that circuit. In this case, we're shorting out the 20 ohm resistor here, and so it's just not included, not considered in the analysis. Calculate the current flowing in the short as your RN, and then the same as the Thevenins, the Norton's resistance is looking back in at the two terminals A and B. So we calculate that in the same way, in this case 4 ohms, and we can then use those values in the equivalent circuit to find the load current and the power, and we can find the terminal voltage as well if we wanted to. Alright? All happy with that? Yeah? So you now got those two techniques, Norton's and Thevenin's, to be able to use. What we're going to do now, or for the remainder of the session, right guys, lab, I'll just do a quick run through with you, okay, and then you can make a start. So in this lab, what you're going to do is, I'm going to go back row, Tom and Jake do Thevenin's. Oh, hang on. No, 4 on the back, and Jake, sorry, Thevenin's. Remaining 4 Norton's. Okay. If you then have time, you can always do both. All right. So in this lab, you're going to use either Thevenin's or Norton's theorem to analyze a given circuit. Okay. Circuit has dual sources, so you'll also need to use superposition theorem to find either the current, the Norton current, or the Thevenin's voltage. Okay. After completing the necessary calculations, so you're going to do your calculations first, right? Then you're going to use the quite universal circuit simulator that we introduced last time to confirm those results. Alright, so first of all, on the second page of your handout, you've got the complete circuit that you're going to analyse. So for the circuit of figure 1, use either Thevenin's or Norton's theorem to calculate the load current RL for the following resistor values: 15, 33 and 56 ohms. Hint, you may need to use the superposition theorem to help calculate the open circuit voltage for the Thevenin's theorem, or short circuit current for Norton's theorem. Record the results of your calculations in the table on page 7. So right at the end, I've included you a table where you can record all the results in one place. There. So top row is the results of calculations, either via Norton's or via Thevenin's. Okay? Then what you're going to do after you've done that is fire up the simulator. So as I've left you a full page for calculation, complete white page, keep everything together, and then you're going to set up on the simulator the complete circuit as it stands. Okay, and we're measuring a current probe in a load resistor leg, and I put a voltage probe across the load resistor so you can measure the load current and the load voltage. We've got two sources of voltage here, 12 volts and 10, and two resistors. So set up the circuit like that, DC simulation, okay, and record the results of the complete circuit. Everybody happy so far? And again, those results as a column for that in your results table. Then you're going to either set up the Thevenin simulation. So here I've got Thevenin's voltage, Thevenin's resistor. Note the values in the picture are not what you're going to be using. You're going to calculate those. Okay, so that would be your Thevenin's voltage. There's your Thevenin's resistance in series. I've put a current probe in series as well. I've got my load resistor, which I can change to the 3 different values. Okay, and I've got a voltage source there. Again, run a DC simulation and compare the 3 results for the 3 resistors you've got with that we've got for the complete circuit. And they should come out exactly the same. Yeah. And then if you're doing the Norton circuit, you will build the Norton circuit as there. You may find that you've got to do both. Okay. And then there's a little extra I might get some of you to do, or all of you to do, if we have time. All right. Everybody happy with that? Good.